All right, flip side of the resonance coin, formal charge. They go hand in hand. When you're doing resonance structures, you do formal charges. Although we can apply formal charges to anything. Because remember, resonance structures have the same skeletal structure, same atomic placement. It's just multiple bonds kind of differ, and lone pairs kind of differ how you distribute those valence electrons. And so formal charges are going to be a way for us to make a distinction on if we have multiple valid Lewis structures or resonance structures, and they're not equivalent, which ones contribute more to the overall structures, right? Which ones, and again, we can't say, hey, it's 70 or 80%. We just say that one will be a better structure or contribute more to the overall structure than that one because they are technically a blend of all. Now, formal charges could be used to check different skeletal structures if you wanted to. You could say, well, I'm not sure where this oxygen goes. Does it go in the middle or on the outside? We kind of try to use our best judgment, and once you've done enough of them, you're usually correct. But sometimes you're like, I'm not sure. Let's do this way and let's do this way. You can use formal charges to double check which is the better atomic arrangement or skeletal structure as well. So we'll do one of both. It takes a while to calculate these when you actually show out the calculation. So I'll do that one time, and then after that, we're just going to do it in our head. All right, just write the back because it takes forever. So I'll give you an equation for this. But technically, what is a formal charge? It's a lot like an oxidation number, but they're a little bit different. So formal charge is a numerical value, a +1, a -2, a 0, some numerical value that represents the electronic environment an atom is feeling or experiencing in some kind of structure, right? So what's the carbon atom feeling electronically in the carbonate ion versus the carbon atom in a methane molecule versus carbon in carbon dioxide, right? Different environments. So if that carbon in the center is surrounded by lots and lots of highly electronegative atoms that are pulling electrons away from it, that carbon is kind of feeling kind of positive because all of its electrons are being pulled away. But if carbon's surrounded by more non-electronegative elements like hydrogen, it's retaining more of its, bonding electrons, so it's not going to be quite so positive. See the difference? Or it could be negative if you have a really highly electronegative element that's pulling electrons towards it by the surrounding atoms around it. So you can get negative values as well. So negative values feel a little more electron charge, positive values a little bit less. So you can kind of get the feeling that more electronegative atoms tend to have, negative formal charges or 0. And we're going to find out 0 is the preferred state. And then less electronegative elements prefer 0. If not, they end up being a little bit more positive. A formal charge emphasizes the covalent character of the bonding, all right? Whereas an oxidation number emphasizes a little more the ionic character. So they have the same idea, but different approaches, all right? So we're going to focus on formal charges. Let me give you an equation on how to calculate that. There's a shortcut to it, but let me give you the equation. Here is your crazy equation. Let's talk about it. So the formal charge, you look at a Lewis structure and you look at a single atom of a single element in there, right? So like with carbonate, you can look at the carbon, oxygen number 1, oxygen number 2, or oxygen number 3. It doesn't matter if what element it is. It depends where that element is and what it's bonded to. So I could have 3 oxygen atoms in a Lewis structure, each with different formal charge values based on the bonding. Right? So you can't just say all oxygens are, you can't assume all oxygens are this, or all, all nitrogens are this, or all carbons are this. It all depends. So you have to do them all individually. That's why they take forever. So what's the formal charge, or FC, on an individual atom, whatever element it is, in some specific Lewis structure? What we're going to do, we're going to say, well, how many valence electrons are there on the free atom, which we've been doing. Whoops, if I held that straight up. So 1 valence electron, 2, 3, 4, 5, 6, 7, 8. So fluorine would have 7, oxygen 6, phosphorus 5. So you just take, hey, if I had the free atom by itself, how many valence electrons would it have? There you go. Just that equal to the group number. We're going to subtract from that all of the electrons it counts for itself, sort of, when it's sharing. So a non-bonding electron, the lone pairs, it's not sharing with any other atom, is it? So we can count all of those for itself. Hey, that lone pair is mine. If I have 2 lone pairs, all of them are mine. So 1 lone pair would count as 2 electrons, 2 lone pairs would count as 4 electrons. You just count the dots in Lewis structure. So all of the non-bonding electrons or lone pair electrons, it counts for itself. And then we're going to subtract half of the bonding electrons. So if there's a single bond with another atom, right, that's 2 electrons, but it can only count 1 because technically it's sharing. So a double bond has 4 electrons, so it would count 2, and a triple bond 6 electrons, so it would count 3 for itself, right? So you just count up the total number of bonding electrons and multiply it by half, and that's it. So these are the total number of electrons it counts for itself. So how many does it have on the free atom? How many does it have on the atom in the bonding situation it's in for that Lewis structure? That difference will tell you its formal charge. So if the number of valence electrons on the free atom is equal to the number of electrons it can count for itself in the Lewis structure, then those are the same. That would be 0. That's the best scenario. That's a situation where it's in its happiest state electronically, right? And then the further from 0 it is, the less happy it is, whether negative or positive, right? Because you could either have more electrons than the free atom or less electrons, giving you negative versus positive. So here's some rules or tips when you have multiple non-equivalent or any Lewis structures, but we're mostly going to use this to discern which are better for non-equivalent, a bunch of non-equivalent resonance structures, which is the better one and contributes more. That's mostly the use. So this is a rule for all of them. The sum of the formal charge values on every single atom in that Lewis structure, atom all together, has to equal the overall charge of that structure. So like I said, the carbonate ion was a -2. So if you add the carbon plus oxygen 1 plus oxygen 2 plus oxygen 3, all those formal charge values, that better equal -2, right? For HOCN, that was cyanic acid, that was neutral. It was 0, right? So the hydrogen plus the oxygen plus the carbon plus the nitrogen had better equal 0. It has to. If it doesn't equal, something's wrong. Either you miscalculated a formal charge or your Lewis structure is wrong. One of those two. So once you've passed that test, then look at all the formal charge values. The closer to 0, the better, with 0 being best. So if I have 2 equivalent structures, and one of them has a value of 0, 0, positive 1, and the other one is a 0, -2, positive 1, right? You're like going, well, that value, -2, is way too far away from 0. That's highly unlikely. The ones with the +1s, -1s, and 0s is better than one with +1s and -2s and stuff like that. One with all 0s wins automatically. If every atom in that Lewis structure has a formal charge of 0, bingo, you have a winner. It's kind of hard to beat that one. So the further from 0, either in the positive or negative direction, the worse that structure is, like the less that structure is going to contribute, right, to the overall, like resonance structure or something, the overall structure of the molecule. All right. Now, if you're having trouble discerning which one might be better, maybe all the formal charge values are equivalent, right? You have a 0 + 1 - 1, and another one has a 0 + 1 - 1. But the +1 - 1 are on different atoms. But they're all the same numerical, value, so you can't discern which is better based on the second step. Then you have to go to the third step and fourth step. So it's unlikely, I guess possible, but highly unlikely to have two exactly the same formal charge values on adjacent atoms. So like a +1 + 1 0. That's highly unlikely to see. I guess it's possible, but not favorable. So 2 -1s next to each other, probably not likely. And this last one, like I said, if you have a situation where the values are the same, they're just on different atoms, the better one has the more negative formal charges on the more electronegative elements because they tend to draw electrons towards them. The more positive formal charge values tend to go on the less electronegative atoms because they tend to not want those electrons around them. So they tend to like to be in a more positive environment, versus the more electronegative ones tend to like to be in a more negative environment, preferably 0, but if they have to have one, a -1 would rather go on a fluorine than on a carbon or something like that if you have options. So that's a lot to think about. Let's do it. You just learn better when you actually do it, right? So keep these in mind. These are very important. Very rarely will you run into the third one. We don't have to use the fourth one often, but right, if we do, that's an arrow in our quiver. Usually you're good with just the first 2. Let's do one that looks at the difference in atomic connections, and then let's look at one where we can determine the more likely or the highest contributor of a series of non-equivalent resonance structures. Whew. It's going to be a lot of calculations, gang. All right, let's take a look here. And the purpose for this one is to show you that when you're doing Lewis structures, there's always kind of exceptions. All right, and this is going to be something where I'm going to show you two situations where we can use formal charges to help us get a better Lewis structure than we would anticipate. So let's take chlorous acid, HClO2. I left the equation for calculating formal charge up on there. Number of valence electrons, if you go through, you got the hydrogen, chlorine, and 2 oxygens, you get 20. 6n plus 2, n is 3, so 18, 19, 20, 20 minus 20. We predict all single bonds here. I'm going to show you where this can lead you astray for some examples, some specific scenarios. Here we go. Now, another issue with the way general chemists versus organic chemists write the structures of oxyacids, right? So general chemists like to put the hydrogen in the front, whereas organic chemists typically go ClO2H. Oh, I got to go into the camp of organic chemists. They do it more correctly. So the way this looks, it looks like the hydrogen's bound to the chlorine, doesn't it? It's actually bound to the oxygen. It's an oxyacid. Let's do the two Lewis structures and show you why this is better with the hydrogen bound to the oxygen. So let's go like this. Let's do the hydrogen, chlorine, oxygen, oxygen. Right? Remember, we don't want the two oxygens bound together. So 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8. So now let's do that versus, let's put the hydrogen on the oxygen. So does the hydrogen go here or there? It's a deceptive formula. All right. So now let's do it this way. We'll do the chlorine with the oxygens. Make this a little smaller. Ooh, that's an ugly looking chlorine. There. This is actually more correct. That's why it's called, again, why it's called an oxyacid. So 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8. Right. Hopefully you can see oxygen prefers 2 bonds, and here that has 2, here neither of them do. So, but chlorine wants 1 bond, so it's not happy in either scenario, but this is a little closer. We can represent that with formal charges. So let's do the formal charges in purple. You ready to calculate these? So let's do the hydrogen. All right. So I'm just going to write them here and then erase them as I go to the next atom. So this for the hydrogen. We know hydrogen has 1 free atom, right? It's in group 1. 1 electron in the free atom. Well, do you see any non-bonding electrons there? No. And how many bonding? There's 2 bonding electrons times half is 1. So that is equal to 0. Right? So hydrogen has a formal charge of 0. It wants 1 bond and it has 1 bond. So it's kind of happy where it's at. Let's do the chlorine. Chlorine has 7 valence electrons in the free state, right? How many non-bonding electrons does it have? 2. Well, how many bonding electrons does it have? 2, 4, 6. What's half of 6? 3. So what's 7 minus 5? Plus 2. So the chlorine here has a plus 2 formal charge. Everybody good? You can probably do this in your head. Let's do this oxygen here. Right there. Right? Oxygen has 6 valence electrons in its free state. It has 2, 4, 6 bonding electrons. So let's subtract those 6. And then it has 6 non-bonding electrons, right? And then 2 bonding electrons times 1/2 is 1. So 6 minus 6 is 0. Minus that is -1. So that oxygen has a -1 formal charge. It's got 1 bond less than it would like. So that's going to be a -1. Pretty good. Let's do this oxygen here. 6 in the free state, right? Oops, I'm missing a lone pair, aren't I? It would help if I had the octet rule, right? So this one will be 6 minus 2, 4, 6, minus half of 2 is 1. That is also a -1. Is that a surprise? They're both oxygens with a single covalent bond and three lone pairs. They're in the exact same electronic environment bonded to the chlorine, so they're going to have the same formal charge. So if you wanted, you could have just went both oxygen atoms, boom, and done the calculation. All right, let's add these together. -2 plus 0 plus -1 plus -1 is 0. The sum is 0, and it's a neutral molecule. Hey, all right. But it has these high formal charges, very unlikely. Let's do the formal charges for this one where we drew the hydrogen on the oxygen. Okay, this usually won't be an issue, but if you're not sure where the atomic placement goes, you can do this. Now, these oxygens are different. Do you see it? This has 1 bond and 3 lone pairs. That has 2 bonds and 2 lone pairs. Those are different. Let's do the chlorine here. So we got 7 valence electrons. We've got 4 non-bonding electrons. And 2, 4, half of 4 is 2. So the chlorine is a +1 there. Can you see the chlorine is better with a +1 than a +2? It's closer to 0. So the chlorine's much happier in this environment than that environment. Let's look at this oxygen right there. Well, that's the same as these, right? 3 lone pairs and 1 bond, so that's going to be the same as that, so we don't have to recalculate it. Let's do this oxygen. We've got 6 valence electrons in the free state. How many non-bonding electrons? 2 plus 2 is 4. We've got 2 4-bonding electrons. Half of that would be 2. It wants 2 bonds and it has 2 bonds, so it has a formal charge of 0. All right, much better. See, instead of a -1, now it's a 0. Much better. Hydrogen is in the exact same state here, right? Hydrogen's always going to be a 0. It has to be. So can you see that this is better? Because it has the lower formal charge values. But I wanted to make the point that when we draw the molecular formulas for oxyacids, in general chemistry we don't do it correctly, but we like it because it shows that it's an acid. We like to put the acidic hydrogen in front, but really this should be drawn like this. That would be more technically correct. Kudos to the organic chemists, right? But watch this. Watch this. Remember, we predicted all single bonds, but life isn't so nice. We have a situation here. Wouldn't it be nice if it could get to a 0 formal charge? So watch what happens here. What if we took that lone pair right there and stuck it in between the chlorine and the oxygen? It wasn't predicted from here, but watch what happens. This happens with sulfate and phosphate and all this weird stuff. So we've got the chlorine, exactly like we did before. But now we poured this lone pair into a double bond. We wouldn't anticipate that, but watch what happens when we do this. Let's look at the formal charges. You ready? This oxygen now has a double bond and 2 lone pairs. You see that? It's exactly like this one. So that has a formal charge of 0, because that's going to be 6 minus 4 minus half of 4 is 2. Oh, so it went from a -1 to a 0. Oxygen loves to have 2 bonds and 2 lone pairs. That hydrogen, of course, is a 0. This oxygen, of course, is a 0. That hasn't changed from that scenario. Let's look at the chlorine now. See, chlorine was a +2 here with a hydrogen in the wrong spot. +1 there, better, but watch what happens. Let's do the chlorine. 7 for the free atom. It has 2 4 bonding electrons, right? I mean non-bonding electrons. How many bonding electrons does it have? 2, 4, 6. So what's half of 6? 3. That now has a formal charge of 0. Oh, 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 oh. This is the best structure. Do you see that? Now, why did that not get predicted? This will happen, like I said, with a lot. There's some exceptions to what we've been doing. The sulfate. So a lot of the third row, n equals 3, chlorine, sulfur, a lot of these babies right in here. They end up getting expanded octets that you wouldn't anticipate in order to lower the formal charges to 0 or closer to 0. See how that worked out? Now, why does this not predict? Okay, let's think about this. You ready? Let's erase these. I won't give you too many of these on exams, right? Because then you gotta, I just kind of leave it with this. I give you ones that work every time with that one. But in real life, there's some weird things. Let's take a look here. In this scenario, we've got a double bond, right? What would a double bond be here? It would be a +2. That's what we would have calculated for a double bond. But we have 2, 4, 6, 8, 10. We have an expanded octet, right? By 2 electrons. So that would give us a value of -2 up there. What's +2 plus -2? See why you get a value of 0 there? The expanded octet you actually have gives you a -2 for the 6n plus 2 minus valence electrons. And the double bond, the extra multiple bond, will give you a +2. And the +2, -2 cancel out and give you a 0. Oh, that can happen sometimes, right? When we did the NO free radical, we had a +3. We had a double bond and an electron deficient species. So welcome to real life. On my exams, that's not going to happen. It's going to be one of the possibilities. I'm not going to give you conflicting things that cancel out like this kind of situation. But I want you to understand, yes, that can happen. And we predicted it with formal charges, right? We're like, whoa, we wouldn't have anticipated an expanded octet on the chlorine with a double bond there. But by doing it, it still matches that, but it wasn't intuitively obvious. Let's look at non-equivalent resonance structures and show you which one contributes most to the overall structure. Tricky, tricky. So especially like sulfate and phosphate and stuff, they have so many more double bonds and expanded octets than you would anticipate just by doing the normal thing because they cancel out. Erg. All right, I copied what we had for cyanic acid. So we've done the 3. Remember, we had 3 possible Lewis structures, all valid. But it turns out they're not equivalent. It's not like carbonate or ozone. Carbonate, ion, and ozone have equivalent Lewis structures, so they all contribute equally to the overall structure. Whereas here, they're not. These are all valid again. We proved that in the last one. Octet rules satisfied, duet rules satisfied. They all have 2 multiple bonds. They're all good to go. But we have 3 possibilities here that are not equivalent. So one of these is going to contribute most to the overall structure, and then another one, then another one. We can't do percentages, but we could definitely tell based on the one that has the formal charges closest to 0, ideally all 0. So what I want you to do is take this equation, just like we did for chlorous acid. You're not going to get any weird business here where it expands, you get an expanded octet and a double bond that you didn't anticipate. That's more rare. Do the formal charges for the hydrogen, oxygen, carbon, nitrogen for all 3 of these Lewis structures. So pause it, go through the calculations. I'm not going to show the work for this. I'm just going to go through and do it. Are you ready? So we'll just walk through it together. So hydrogen, 1 minus 0 minus half of 2, which is 1, means that hydrogen has a formal charge of 0. Yeah, it always does. It has 1 bond, it wants 1 bond. It's good to go. This oxygen has 6, right? I'll just do it down here real quick. So 6 minus, how many non-bonding electrons? 2 minus half the bonding. 2, 4, 6. Half of that is 3. So it has 1 more bond than it wanted. Right? We good with that? Let's do the carbon. 4. Right? That's how many is in the free atom. There's no lone pairs on there. Minus half of 8 is 4. You're very commonly going to get carbon in a 0 state all the time. because it wants 4 bonds. And if it has 4 bonds, it's going to be a 0, right? Pretty much if it has its preferred number of covalent bonds, it's a 0. Let's look at the nitrogen. So the nitrogen will be 5 in the free state minus 4 of the non-bonding electrons. And then half of 4 is 2. So that'll be a -1. So it wants 3, but it has 2, so it's kind of missing a bond. So 0 plus 1 plus 0 minus 1. The sum is 0, right? And it should be. It's a neutral molecule. So the sum of the formal charges should be 0. It's a way to check yourself. Okay? So that's not too bad. We got 2 atoms in their preferred place and 2 that are just 1 step away. Let's do this one. Hydrogen's pretty much always going to be a 0. 1 minus half of 2, which is 1. 1 minus 1. Let's do this oxygen. Hey, here is a +1. Let's do the oxygen. 6 in the free state. We've got 4 non-bonding electrons. Half of 4 is 2. So that oxygen's a 0. Ooh! Oxygen's much happier with 2 covalent bonds and 2 lone pairs. Let's do this carbon. Right? So we've got 4 in the free state. There's no lone pairs. Minus half of 8. Carbon's almost always, if carbon has 4 bonds, it's probably going to be a 0, right? Let's do that nitrogen. 5 in this group 5A. It's got 2 non-bonding electrons. 2, 4, 6. What's half of 6? That's 0. 5 minus 2 minus 3. So nitrogen's a 0. It has 3 bonds. It wants 3 bonds. You can do these pretty quick. Whoa! All 0. Bing, bing, bing. We know that's going to be the winner, right? Unless this is all 0, but it's probably not going to be because it's not that one. So this is better than that one. You see? Let's do it for this. Hydrogen, of course. 1 minus 0 minus half of 2 is 0. Let's do the oxygen. 6 in the free state. There's no non-bonding electrons on there. It's got 8 bonding electrons, so half of that is 4. So that's a +2. So it has 2 bonds more than it wants. Really not. Oxygen really does not like that triple bond there at all. It's like, ew. It'd rather be here, but best there. Okay. This carbon, you see how it's got 4 covalent bonds? So 4 minus 0 minus half of 8. That would be 0. So carbon's happy in every single situation here. Let's do the nitrogen. 5 minus, now there's 6 non-bonding electrons. And there's 2 bonding ones. So what's half of 2? It's 1. So that looks like 5 minus 6, -1, looks like a -2. Let's look at the sums. So the sum of this is 0, right? 0 plus 2 plus 0 minus 2, sum equals 0. So they're all valid Lewis structures, but can you see this is the best one? So this contributes the most, probably some huge percentage. I don't know what it is, some huge percentage. This is not carbonate where they all contribute 1/3. This is the majority of it. Contributes most to the overall Lewis structure. To the point where if you see that on my test, and you can immediately go to one that has all formal charges of 0, I'm okay if you just show me that one. Okay? But if you have a bunch of equivalent resonance structures like carbonate and ozone, you got to show me all of those. But if you've got a bunch of non-equivalent Lewis structures, on my test, that's the only one you need to give me. I'm okay with that. It seems that because nitrogen has 3 bonds, carbon 4, oxygen is 2. It's pretty obvious. This is the worst. Right? Because it's got values furthest from 0. Okay, so best, in the middle, worst. So this contributes most, a little bit from this, and probably hardly any, if at all, that one. That's what formal charges are for. You can calculate them pretty quick, right? And it allows you, so 2 things. It allowed us to determine a better skeletal structure or atomic connection, like with the HClO2. Well, actually 3 things. It allowed us that too, allows you to discern the better of non-equivalent resonance structures. And then we also talked about there are some exceptions to the 6n plus 2 minus number of valence electrons, where things like expanded octets and multiple bonds cancel out. So what you get doesn't anticipate what it really should be. You won't get those on my exams, but you can use formal charges to go, oh, if I gave this an expanded octet and gave that a double bond, I would still get the same result as I did on the 6n plus 2 minus number of valence electrons, but I get a better structure with formal charges closer to 0 or 0. Boom! We can do it.